Welcome all to the course of Data Communication and Networking, B7 semester, Electronics and Communication Engineering. In the last session, we have defined logical address part 1, in which an IPv4 discussion can be done. So for following points, we have discussed decimal notation, binary notation, class pool addressing, net ID, host ID, subnetting and supernetting. We continue our discussion with an IPv4 in this lecture. So let's start with our classless addressing. In the previous case, it is a class full addressing. Over here, we discuss about a classless addressing. To overcome the addressing depletion and give more organizations access to the internet, classless addressing was designed and implemented. In this scheme, there are no classes, but the addresses are still granted in a blocks. So what are the address blocks? In a classless addressing, when an entity, small or large, needs to be connected to the internet, it is granted a block or a range of addresses. The size of the block or number of the addresses varies based on the nature and size of the entity. For example, a household may be given only the 2 addresses. A large organization may be given thousands of addresses. An ISP, as an internet service provider, may be given 1,000 or hundreds of thousands based on the number of the customer it may serve. Fine. So there are address blocks. So what are the restrictions for these address blocks? To simplify the handling of the addresses, internet authorities impose 3 restrictions on the classless address blocks. So these 3 are mentioned over here. The first is the address in a block must be a contiguous, one after another, means 1, 2, 3, 4, 5, just like this, or an incremental order. But second restriction is the number of the address in a block must be a power of 2, just like 2 raised to 0 is equal to 1, 2 raised to 1 is equal to 2, 2 raised to 2 is equal to 4, 2 raised to 3 is equal to 8, means power of 2, means you can say that 2 raised to n power. Third, the first address must be evenly divisible by the number of addresses. Let's clear this restriction with the help of the example. Right? First, example 1. For this, you just see the figure. This figure shows a block of addresses in the both binary and decimal notation. We have already discussed the decimal and the binary notation in the previous chapter or previous lecture. It is granted to a small business that needs only 16 addresses, first and last. We can see that the restrictions are applied in this block. The addresses are contiguous, 32, 33, 10. The number of address is a power of 2. Over here 16 is there, so it is a power of 2 raised to 4. The first address is divisible by 16. The first address is divisible by 16. Fine. The first address, when converted to the decimal number, it will be 3440 387 360 for this. Fine. Which when divisible by 16 result, the result will be 215 024 210. mask. One important parameter to be considered over here is a mask. A better way to define a block of address is to select any address in the block, the call and the mask. As we have discussed before, the mask is a 32-bit number in which the n leftmost bits are ones and 32 minus n rightmost bits are zeros. We have already seen this mask concept in our previous session, in which different class A, B, C, D we have defined. However, in classless addressing, the mask for a block can take any value from 0 to 32. It is very convenient to give just a value of n preceded by the slash, just like our CIDR notation. So in IPv4 addressing, a block of addresses can be defined as x.y.z.t/n, in which x.y.z.t defines one of the addresses and /n defines the mask. The addresses and the slash notation completely define in a whole block: first address, last address, and number of addresses. Okay, so what is the first address? The first address in the block can be found by setting n 32 minus n rightmost bit in the binary notation to the address to the zeros. So we can say that the first address in the block can be found by setting the rightmost 32 minus n bits to zeros. Okay, let's have an example. A block of address is granted to a small organization. We know that one of the addresses is 205.16.37.39/28. What is the first address in the block? In the binary representation, the given address will be 204.205.16.37.39 will be converted to the binary. As you can see, it is a binary conversion of a 4 digits. If we set 32 minus 28, because the n value is 28 over here, the rightmost bits to 0 we get over here. 32 minus 28 will be 4, means last 4 digit will be 0. So over here put 4 zeros over here. Fine. Or it will be in a decimal notation 205.16.37.32. Fine. So it is just a block shown in our figure, as you can see over here. So 105.16.32. Fine. So it is our first address. So what is the last address? The last address in the block can be found by setting 32 minus n rightmost bit in the binary notation to the address to the ones. So as you can see, the last address in the block can be found by setting the rightmost 32 minus n bits to ones. Let's have an example for the same. So find out the last address for the block in example 6.6. So what is the address? 105.16.37.39/28. So we just find the last address for the same. Over here, the binary representation of a given address will be this. If we set 32 minus 28 rightmost to 1, we get, so last 4 will be 1. So already 3 ones are there, or 1 is added. So our address will become like this. If we convert into the decimal notation, the last 2 digit will be 47 in the place of 39. Okay, so over here you can say that it is an actually a last address shown in our previous figure. So you just verify your address 205.16.37.47. Okay, so it is a last address. Now a number of addresses. The number of address in a block is a difference between the last address and the first address. It can easily found using the formula 2 raised to 32 minus n. Okay, so let's have an example for the same. Find the number of addresses in our previous example. So the value of the n is over here 28. Fine, so which means that the number of address will be 32 minus 28 is equal to 4, and 2 raised to 4 will be 16. So it is verified and it is proved that the same block have a 16 addresses. Another way to find a first address, last address and the number of address is to represent a mask as a 32-bit binary or a 8-digit hexadecimal number. This is a particularly usable when we are writing a program to find these pieces of information. In our example, 8 can be represented as over here 28 ones and 4 zeros, 28 ones and 4 zeros. So find the first address, last address and number of addresses. So what is the solution? For the first address, it can found by ending the given address with the mask. Ending here is done by the bit by bit. The result of ending 2 bits is 1 if both are 1. The result will be 0 otherwise. So it is our address of our previous example. The mask will be like this, all ones and last 4 digit is 0. So the 4 is the first address. The ending of 2, 1 into 1 is equal to 1, 1 1 1, 0 into 1 0, 0 into 1 0, 1 1 1, 1 1 1, 0 into 1 0 and 1 1 is 0. Same can be done to find the first address. Okay, the last address, it can be found by ORing the given address with the complement of the mask. ORing here is done bit by bit. The result of an ORing 2 bits is 0 if the both are 0. The result is 1 otherwise. The complement of the number is found by changing each 1 to 0 and each 0 to 1. Means a mask will be alternate. All ones will be converted into 0 and 0 will be converted into 1 over here. Fine, a mask complement. So what is the ORing? If any of the two element will be 1, our result will be 1. If both are 0, our result will be 0. So you can observe that it is a 0, it is also 0, over here 1 is 1. Okay, the same can be found. So the number of address can be found by complementing the mask and interpreting as a decimal number and adding 1 to it. Means a mask complement will be all zeros and only 4 ones are there. So what is the value of this? 1, 2, 4 and 8. 8 plus 4, 12. 12 plus 2, 14. 14 plus 1, 15. 15 and add one thing in this, we find the total number of addresses be 16. Okay, so you can find first address, last address and number of address with this method also. A network addresses. A very important concept in our IP addressing is the network addresses. When an organization is given a block of addresses, the organization is free to allocate the addresses to the device that need to be connected to the internet. The first address is the class, however, is normally treated as a special address. A first address is called the network addresses and defines the organization network. It defines the organization itself to the rest of the world. In the later chapter, we will see that the first address is the one that is used by the routers to direct the message sent to the organization from the outside, means a default address. Our figure shows an organization. This figure shows an organization that is granted in 16 blocks. Fine. It is a 16 blocks. We have already seen the same address will be there and the same example. Okay. The organization network is connected to the internet via a router. It is a router. The router has two addresses. One belongs to the granted block and other belonging to the network that is at the other side of the router. We call the second address as over here x.y.z.t/n because we do not know anything about the network. It is connected with the other side. All messages destined for the addresses in the organization block, just like our 205.16.37.32 to 105.16.37 to 47 are sent directly or indirectly to the x.y.z.t/n. We say directly or indirectly because we do not know the structure of the network to which the other side of the router is connected. The first address in the block is normally not assigned to any devices. It is used as a network addresses that represents the organization to the rest of the world. So, okay, you can see over here. Over here, a first address is not used by any other devices. So, what are the hierarchy? An IP addresses, like other addresses or identifiers we encounter these days, have a level of hierarchy. For example, a telephone network in the North America has 3 levels of a hierarchy. The leftmost 3 digits define an area code over here. The next 3 digits define the exchange office, and the last 4 digits defines the connection of the local loop to the central office. This figure shows the structure of a hierarchical telephone number. So first 3 digits is area code, then after exchange office number and a subscriber number. So what are the 2 level hierarchy? There is no subnetting over here. An IP address can define only the 2 levels of hierarchy when not subnetted. Means subnetting is not there. The leftmost bits of the addresses of XYZN/ defines the network, just organization network. The 32 minus n rightmost bit defines a particular host, computer or router to the network. The 2 common terms are prefix and suffix over there. The part of the address that defines the network is called as an prefix. Fine. Network prefix. You can say that it is a network prefix. The part of that defines the host is called as an suffix. Or you can say that host address. This figure shows the hierarchical structure of an IPv4 address. The prefix is common to all the addresses in the network, then the suffix changes from one device to another. So you can say that each address in the block can be considered as a 2 level hierarchical structure. A leftmost n bits, just like our prefix, defines the network, and the rightmost 32 minus n bit defines the host. Next is 3 level of hierarchy, just like using a subnetting. An organization that is granted a large block of an address may want to create a clusters of a network called as a subnets, as highlighted over here in a different color, and divide the address between the different subnets. The rest of the world still sees the organization as a one entity. However, internally there are several subnets. All messages are sent to the router. We have an address that connects the organization to the rest of the internet. The router routes the message to the appropriate subnets. The organization, however, needs to create a small sub-blocks of an address, each assigned to a specific subnets. The organization has its own mask. Each subnet must also have its own. As an example, suppose an organization is given a block just like a 17 12 40 0 17 12 40 0/26, which contains a 64 addresses. Means 32 minus 26 will be 2 raised to 6 is equal to 64. The organization has 3 different offices and needs to divide address into the 3 sub blocks, just like 32, 16 and 16 address. So it will be 32, 16 and 16. We can find a new mask by using the following arguments. First, suppose the mask for the first subnet is n1, then 2 raised to 32 minus n1 must be 32, which means that n1 will be 27. Suppose that the mask of the second subnet will be n2, then 2 raised to 32 minus n2 must be 16, which means that the n2 will be 28. Suppose the mask for the third subnet will be n3, so 2 raised to 32 minus n3 must be 16, which means that our n3 will be 28. So you can see that one have a subnet mask where have a n1 is 27 and remaining are 28 over here. This means we have a mask of 27, 28 and 28 with the organization mask being 26. Our figure shows one configuration for the above scenario. Let us check to see if we can find the subnet address from the one address of the another in the subnet. So in subnet 1, the address is 17 12 14 29/27 can give us the subnet address if we use the mask 27, because the host will be just like this. The mask will be 27, the subnet will be just like this. Note that applying the mask of the network /28 to any of the address give us the network addresses 17 12 14 0/26. We can say that through the subnetting we have a 3 levels of hierarchy. Note that in our example the subnet prefix length can differ from the subnets, as you can see in this figure. In subnet 1, 26 bits, then network it is a network prefix, it is a subnet prefix, and our host address. Over here 26 will be network prefix, then a 2 subnet prefix. After a host address have 4 bits. So you see the difference in the last 2 departments. So what is a scenario where the levels of hierarchy are more. The structure of the classless addressing does not restrict the number of hierarchical levels. An organization can divide the granted blocks of an address into the sub-blocks. Each sub-blocks can in turn be divided into the small sub-blocks, and so on. One example of this is the seen in our ISPs. Our national ISPs, our national IP can divide a granted large block into the smaller blocks and assign each of them as a regional ISPs. Let's take an example of our country, that our Indian territory will be divided into different states. So our national ISP will India, and take a regional ISP will be our Gujarat. And our regional IP can be divided blocks received from the national ISP into the smaller blocks and assign each one to the local ISP, just like our different districts of a Gujarat. So the local ISP can divide blocks received from the regional ISP into the smaller blocks and assign each one to the different organization. Finally, an organization can divide a received block and make several subnets out of it. Okay. Next is address allocation. The next issues in the classless addressing is an address allocation. How are the blocks allocated? The ultimate responsibility of the address allocation is given to a global authority called as an International Corporation for Assigned Names and Addresses, ICANN. However, our ICANN does not normally allocate addresses to the individual organization. It assigns a large block of an address to an ISP. Each ISP in turn divides its assigned block into the smaller sub-blocks and grants the sub-blocks into its customers. In other words, an ISP receives one large block to be distributed to its internet users. This is called as an address aggregation. Many blocks of address are aggregated in one block and granted to one ISP. Let's have an example for this. An ISP is granted a block of address starting with 190.100.00/16, just like 65,536 addresses. The ISP needs to distribute this address to the three groups of a customer as follows. The first group has 64 customers, each needs 256 addresses. The second group has 128 customers, each needs 128 addresses. And the third group has 128 customers, needs 64 addresses. Design the sub blocks and find out how many addresses are still available after this allocation. For this solution for the example, you consider a figure over here. Fine. For group 1, for this group, each customer needs 256 addresses. This means that 8 log 2 base 256 bits are needed to define the host, just like 8 bits. The prefix length will be 32 minus 8 is equal to 24 over here. So 24 will be written over there. Okay. So the total 64 into 256 is equal to 16,384. For group number 2, for this group, each customer needs 128 address, and this means that 7 log 2 base 128 are needed to define each host. So 32 minus 7 will be 25. So our mass will be 25, and the total number is 128 into 128 is equal to 16384. The same of our previous case. What will be the third group? For this group, each customer needs 64 addresses. This means that 6 log2 base 64 bits are needed to each host. So the 32 minus 6 is 26. So 26 are there. So total number will be 128 into 64 is equal to 8192. So number of the granted address block of an ISP will be 65536. The number of allocated address by the ISP will be addition of these 3 will be 40,960, and the number of available address will be subtracting this, we get 24576 are available addresses. Okay, so it is a end of our session. So let's revise our session. We start our discussion with introduction of our classless addressing. We have defined an address blocks and also have a discussion of our restriction of address restriction in our classless addressing. We have an example for the same to make it very clearly. A various mask used by how to find a first address. For the same, we have an example how to find the last address. We also seen an example for the same, and the total number of addresses block in our address by find by 2 raised to 32 minus n formula. Fine. We have an example to find out first address, last address, and number of addresses. Over here we use a different methodology, a masking concept we use. The same can be used for the last address and complement of mask to find a total number of address. After that, a network address is defined with the help of the diagram. Then we have discussed about the hierarchical level. It is a hierarchy for the telephone number. It is a 2-level hierarchy, prefix and suffix. And then we discuss a 3-level hierarchy with a subnetting concept. Okay, we have also discussed the number of hierarchical level with the example of ISP for our India, Gujarat, and various districts. Then an address allocation. We have seen an example for the address allocation. Okay. So it is a question for you. One example is given for your exercise. Solve by yourself and send me your answers for these questions in a group, just like our Google Classroom. We continue our discussion with one and last point in our IPv4 is a network address translation called as an NAT in the next session. So goodbye students, thank you and see you in the next session.